Hello, I'm Lou Bloomfield and this is How Things Work. Today's topic, clothing, insulation, and climate. When you're operating a wood stove or cooking dinner, you want heat to flow from here to there. But there are other times where you want to control and even limit the flow of heat. Say when you're trying to stay warm on a bitter cold day, or when you're trying to make sure your house doesn't overheat during the summer. You want then to find ways to limit the flow of heat by the three familiar mechanisms of heat transfer: conduction, convection, and radiation. So in this section, I'm going to revisit those heat transfer mechanisms and look at how we can control them and limit them. So to start with, conduction. Materials conduct heat. So if you have a hot side and a cold side separated by a material, heat will flow through that material by conduction. And the rate at which heat flows through that material depends on a couple things. First off, on how big the separation is between the hot side and the cold side. The farther you get those two sides away from each other, the more gentle the temperature gradient is between them, and the slower the heat flows. And as a general rule of thumb, if you double the spacing between the hot side and the cold side, you have the heat flow through them. All right, that's one. Second thing is reduce the extent of the heat, cool down the hot side, warm up the cold side. Change the temperature difference, make it smaller. And again, as a general rule of thumb, the smaller the temperature difference between hot and cold, the less heat flows through it. And it's roughly proportional, the heat flow is roughly proportional to that temperature difference. All right, next thing, the surface area of the two surfaces that you're letting heat flow between. The bigger those surfaces are, the more path there is for the heat to flow through. And here too, the heat flow is roughly proportional to the surface area between the hot side and the cold side. All right, that leads us to one last thing, the material itself. Different materials have different thermal conductivities. The metals, particularly copper and aluminum, great thermal conductivities. Heat will roar through those materials from the hot side to the cold side. On the other hand, insulating materials, glass, ceramic, wood, those carry heat less well. They have no mobile electrons, and so they can't carry heat by way of the passage of electrons around between the materials, between the atoms. And so the flow of heat is substantially reduced. But even the better thermal insulators, the poor thermal conductors, are the gases. They don't conduct heat well at all. They have a downside though, because they can move. And so air is a great thermal insulator. In other words, it's a terrible thermal conductor. But because it can move, that is an issue, because when it does convection, it can carry heat pretty effectively. So if you can keep it in place, the gas is a great thermal insulator. All right, so that's conduction. In general, to insulate something against thermal conduction, you want to use rotten conductors of heat, or equivalently, great insulators against thermal conduction. And you can first, throw out the metals. They're a problem. They conduct heat too well. There are a few insulators that are in that same category too, like diamond. But diamond isn't something we're going to generally be using to insulate things. So it's a little expensive for that purpose. But in any case, diamond is actually a pretty good conductor of heat. So set it aside too. The rest of the stuff, the solid materials, pretty good to start with, but you can actually do better. And the thing you do better is gases. So as we will see in a minute, gases are among the best of the insulators that we normally work with. All right, that's conduction of heat. How about convection of heat? Trying to control that, because that's already breathing down our neck here, because the gases make great conductors as long as you can get rid of convection. All right, so how do you get rid of convection? Well, obviously you don't have to worry about convection if you're working with true solids. If you're working with liquids, now you've got convection again. Probably not a good choice for an insulator. But gases, how do you control convection? Well, pin them down. Make it very difficult for them to move. And how do you do this? We'll go back to the world of aerodynamics and the flow of fluids. just as air interacts with passing objects, stationary objects interact with passing air. And if you try to make dust flow through air, as we've already seen that dust has trouble falling through air because it interacts by way of viscous forces, and it barely moves through air under the influence of gravity alone. So if you can have essentially a whole big array of dust or something like dust, it can trap the air by way of the same viscous forces that trap the dust in the air. Well, we don't go to dust, we go to fibers. And so fibrous materials, which are, they have enough substance to them to sort of keep themselves intact. A big cloud of dust is just not going to be something you can hold in place. But a big cloud of fibers you can hold in place. And once you have all those fibers, the air has trouble flowing through them because of viscous drag forces. So the fibers of clothing, what's the real purpose of those fibers of clothing? The clothing itself typically isn't the main insulator. It turns out that cloth, cotton, wool, synthetics, plastics of various sorts, they're pretty good insulators against conductive heat transfer, but they're not perfect. They're not super duper. Air's better. So what you can do is you can trap the air with the fibers. Use the fibers, not as the insulation, but as the way of trapping the air. And our best ordinary clothing insulation is fibrous. It traps air. Hair, same thing. The natural insulation that animals have, their hair, their fur, that's trapping air. It's the primary insulator. And air has a tough time undergoing convection when the density of the fibers is just about right. If the fibers are too loose, there are not enough of them, the air can convect between them. There's not enough viscous drag force around to sort of keep the air in place. If the fibers are packed too tightly, you lose the advantage of having the fibrous structure at all. You begin to have basically matted fibers are basically a crummy solid, and they conduct heat too well. And they've excluded too much of the air insulator. So to get nice insulation against conduction and convection, that combo, keep that under control, use a properly chosen density of fibrous material. And this describes or identifies lots of standard insulation. Sweaters made of fibrous materials, jackets filled with down or something like down, fibrous materials trapping the air. Going off into the world of houses, a lot of the insulation used in modern houses is fibrous. It can be fiberglass, it can be other particular fibrous stuff. One of the issues with housing insulation, of course, is you don't want it to burn or be capable of burning easily. And so some fibrous material burns too well. You don't want to fill the walls of a house with cotton fiber, for example. Untreated cotton fiber burns a little too easily, but the idea is fine. All right, so that's the world of conduction and convection. How about thermal radiation? How do you sort of control the flow of thermal radiation? Well, anytime one surface can see the other surface, and if we want to anthropomorphize the surfaces, if two surfaces can see each other, they can exchange thermal radiation. And the hot one will send more thermal radiation to the cold one than the cold one will send to the hot one. There'll be a bad balance between them, and heat will flow from the hot one to the cold one. And the law governing thermal radiation, what's known as the Stefan-Boltzmann law, observes a couple of things about the thermal radiation emitted by one surface. That radiation from the one surface depends on a couple of things. It depends on the temperature of the surface. And if you look at the temperature on an absolute temperature scale, such as Kelvin, the brightness of thermal power coming off that surface. So if you just turn up the temperature and watch how bright it is in terms of energy per second coming off that surface. Energy per second is power. Also measured typically in watts. That brightness is proportional to the temperature to the fourth power. So increasing the temperature of a surface by a modest amount can quite substantially increase the thermal radiation coming off of it. So when you've got two surfaces, one at a high temperature, one at a low temperature, and these are just normal high and low temperatures, like body temperature and outdoor winter temperature. Maybe these differ by 20, 30 degrees Celsius. The body temperature is radiating considerably more thermal energy at the outdoor surface compared to what the outdoor surface is radiating at the body. They are not exchanging equally. The body loses a lot more, sends out a lot more thermal radiation than it gets back. So it's a net loss of heat. And this is why you can radiate away a lot of thermal energy by being in a cold environment. How do you control that? Well, we'll come back to again, one of them, of course, is not to be able to see the cold environment, put something in between. The other thing is that the Stefan Boltzmann law has another piece to it, and that is the what's known as the emissivity, the ability of a surface to emit its own thermal radiation. And different surfaces have different abilities to radiate thermal radiation. A black surface, which is a little bit of a problematic statement. A surface, what does it mean to be black? In this context, a black surface is one that is as efficient as possible at emitting its own thermal radiation. And that may mean that it looks black to your eyes, but it may be, there's more subtleties to it, because the thermal radiation that we radiate as the human animal radiates, we're not very hot, right? We're body temperature is not as hot as the sun. We do not radiate visible light. We do radiate thermal radiation in the infrared. And in the infrared, the question is, how good are we at emitting thermal radiation? It turns out we're pretty nearly perfectly good. That is, we're pretty nearly black objects in the infrared. We're as good as can be at ordinary temperatures at emitting thermal radiation. So our emissivity then is technically almost 1. Emissivity is measured on a simple scale from 0 to 1. 0 means terrible, like infinitely bad at emitting thermal radiation. And 1 means as good as possible at emitting thermal radiation. Black objects have emissivity 1, where black means that the object is as good as possible at emitting thermal radiation. An object that has emissivity 0, that's something that just doesn't interact with its own thermal radiation. So for ordinary stuff, people, the room, at room temperature, near room temperature, body temperature, the thermal radiation that we work with is all in the infrared, and to be terrible at emitting thermal radiation in the infrared, we would need to be either shiny, like a metal, white, which is similar to the light for a metal, but the difference between shiny and white is this. A shiny surface takes the light that hits it and reflects it in a way that remembers where the light came from. So you can see the origins of the light before it encountered the surface, and you see mirror-like reflections as a result. A white surface is one that still sends out all the light that hits it, but it removes any memory of which direction the light came from. So the light that hits the white surface comes back off independent of where it came from. And you can't see an image or any indication where the light came from when you look at the light coming off a white surface. It's forgotten. The last possibility is a transparent surface. Light just goes right through it. And again, it's those 3 possible surfaces, shiny, white, and transparent, have emissivity 0. They're not only unable to absorb light in the same part of the electromagnetic spectrum as their thermal radiation would be, but they're terrible at emitting their own thermal radiation. They can't do it. So a black surface is both very good at emitting its own thermal radiation and absorbing equivalent thermal radiation. A white surface is terrible at emitting its own thermal radiation or absorbing the equivalent thermal radiation from something else. All right, that said then, if you want to reduce your exchange of thermal radiation with the world around you, cover yourself in something that has emissivity 0. By ourselves, we're not emissivity 0, we're more like emissivity 1. So you want to go to 0, wrap yourself up in aluminum foil, which is nearly emissivity 0. Light just comes in, bounces off it. Even infrared light comes in and bounces off it. Not perfectly, but pretty good and pretty well. So aluminum foil will really dramatically reduce your ability to radiate away thermal energy or to receive other object around you, their thermal energy. So that shuts that down. White would be appropriate. Wrapping yourself in white stuff would work too, except most of the white stuff in our world, white cloth, for example, or white paper, it looks white in the visible, which means that white light hitting it comes back off, bounces back off, having lost memory of where it came, but the reflection is essentially perfect. In the infrared, though, the things that we think of as white, that we see as white with our eyes, they're not white in the infrared. They're typically black in the infrared. So most white clothing in the infrared isn't white, it's black. It's unobservable to us because our eyes don't see infrared, but there it is, black. And they are very good at emitting their own thermal radiation and absorbing the thermal radiation of other things that emit infrared thermal radiation. So black, white clothing, not much difference in terms of exchanging thermal energy with the local stuff. That is not true if you're exchanging thermal energy with the sun. The sun is so hot that its thermal radiation is in the visible primarily. It's the light that we can see. And now it does matter what things look like, because their ability to interact with the sun's thermal radiation is something that our eyes can tell us. Black objects, black paint on a car, black paint on or black clothing, those will absorb more thermal radiation from the sun than white stuff, white cars, white clothing. In that case, wearing white is an advantage. If you're going to be exchanging thermal radiation with something that's so hot that its thermal radiation is visible, now you can start paying attention to what your eyes see and choose clothing that is poor at exchanging thermal radiation in this high temperature regime, the temperature of the sun. White is a good choice. Shiny is also a good choice, not necessarily as popular for clothing, but and shiny cars, okay, there's some of that around, but certainly white cars, there are around. In hot climates, white's a popular color. All right, so thermal radiation. How about just now specialize on the insulation of certain things? With people, the insulation that we normally work with are, start with poor conductors of heat if that's a possible choice. And so that's why animals tend to develop fat layers right near their skin. Fat is a poorer conductor of heat than muscle, and so you can get a little bit of advantage to having layers of fat right near your skin. Beyond the skin, trap the air. How do you do that? Have fur, have hair. Wear clothing that traps the air. Wear a down coat that has little fibers, tiny fibers in the down that trap the air. Don't pack the down too tightly, because if you do that, you're starting to look at the thermal conductivity of the down material itself, and that's not so wonderful. Good, but not great. So leave the air trapped, but loose. That's good enough for human stuff. I'll leave that alone now. I suppose you can wear shiny things, shiny jacket if you're trying not to interact with the sun. Anyway, and actually a shiny jacket will also act as insulation against thermal radiation at ordinary temperatures, because typically shiny is pretty good at blocking the transfer of thermal radiation at high temperature of the sun or ordinary temperatures of our environment, ordinary environment. All right, houses. Now, again, you want to use probably fibrous air trapping materials in the walls of houses, the ceilings of houses, anything you can to discourage the flow of heat from hot to cold. And the thicker the walls of the house, of course, the less heat is going to flow between the hot side and the cold side. So thicker walls up to a point. I mean, beyond a certain point, it's just you lose all the interior space of the house. So there are guidelines for how thick the wall should be, how thick the attic, the insulation should be at the top of the house, between the highest heated or cooled portion of the house and the part of the house that's left to the outdoors. Windows are always a big issue. Windows can easily lose a lot of heat. A single pane, the old-fashioned windows, which is just a single pane of glass, was a terrible heat loss, because you would have the outdoor temperature and the indoor temperature only millimeters away from each other on the opposite sides of that single pane of glass. And glass is not a good conductor of heat, but it's not a terrible conductor of heat. And so you got a lot, high temperature on one side of the glass, low temperature on the other, heat goes roaring through it, and the bigger the glass pane is, the more heat flows through it. So potential for a lot of heat flow. How do you solve that? Well, one solution, the most straightforward solution, is to use 2 panes of glass. Not 1, but 2. Now, you can get hot, one pane of glass can become relatively hot by way of conduction through it. The other pane of glass can become relatively cold by conduction through it. So you've got 2 panes of glass, each of them at the temperature of the air beyond them, more or less. I don't know which one's indoor and which one's outdoor. It depends on whether we're talking about summer or winter. But there those 2 panes of glass are. And between them, air or a gas, some other gas. Now, how does heat flow between those? Well, if the air would just stay still, there's not a lot of heat flow between them, because air is a terrible conductor of heat. So if you can trap the air, great. Well, you can't trap the air and still have a good view from one window to the other. So people suffer with the fact that you can't quite put fibrous material in there to keep the air from convecting. However, for windows that are arranged vertically, which most windows are, the air convects vertically. Natural buoyancy lifts the air on the heated side, the hotter side, up all the way to the top of the window, and then it descends all the way down the cool side of the window. It's a giant convection cell going the entire height of the window, and there's a lot of rubbing of that air against, first of all, against itself as it flows in opposite directions, and against the 2 windows. So it has trouble doing this convection. And so the convection inside a vertically oriented window is modest, not a great carrier of heat. If you tip the window horizontally and make a skylight out of it, now you got a problem, because the hot air rises and cool air descends locally. You get little convection cells and now this skylight, and they carry heat much better. And so skylights are a much bigger heat sink than vertically oriented windows. All right, that said, now we've got 2 windows, 2 panes staring at each other. They don't carry heat very well by conduction or convection. How about radiation? Well, alas, here they can do a good job. They are both essentially black in the infrared, which is the relevant regime of the electromagnetic spectrum for this story. And so they exchange thermal radiation just fine. The hotter one radiates more energy, more power at the cold one, and the cold one radiates the hot one, and heat flows. It's a disaster. What do you do? Well, what modern windows do is they coat the interior surface of one of the panes with a reflective material. Now, they could coat it with an ordinary metal, and then they would make great insulation. The one pane would see its own reflection in the metal and therefore see its own thermal radiation coming back at it. The other pane would basically just not speak thermal radiation. It's protected by the shiny surface. Of course, a metal coating on one of the surfaces of the window is hard to see through. So, you're stuck. Not quite. There are materials that are electrically conductive and that are reflective, therefore, in the infrared, but transparent in the visible. They're a strange sort of metallic-like material that is transparent in the visible, but shiny in the infrared. And the physics of that is complicated. But these are the materials that are used as electrical carriers of electricity in a lot of visible things, like liquid crystal displays, like most television sets, computer screens, cell phones. What are you looking through when you see the pixels show you images? You're looking through conductors, things that conduct electricity, but they are transparent conductors. They carry electricity, and they are therefore shiny at low frequencies like radio waves and microwaves, and even in the infrared, but they are transparent and visible, so light comes through. That said then, modern low emissivity windows have one of the surfaces of of the double pane or even triple pane windows, one of the surfaces is shiny. It's coated with a transparent conductor that makes it very hard for the 2 panes or 3 panes to exchange thermal radiation. So you get, yet again, better thermal insulation. Okay, I'm going to leave the world of clothing, the world of house insulation and building insulation stuff, and go on to climate, which seems to sort of come out of the blue as a totally separate subject. But here too, the issue is controlling the flow of heat. And the way our planet works is this, that let's temporarily imagine that we live on a planet with no atmosphere, just the ground. And if the planet were like this, then over time the planet would have heated up to a certain temperature at which it has reached thermal equilibrium. And what's the equilibrium that I have in mind here? Well, the Earth receives thermal energy, heat, from the sun. And if it kept receiving that heat from the sun and did nothing with it except accumulate it, the Earth would get hotter and hotter and hotter indefinitely. Well, that's not the case. Even, again, I'm thinking hypothetically that just a simple Earth with no atmosphere. The sun heats up the Earth, but the Earth has something it can do with the heat. It can radiate that heat out into space, which is essentially radiates back virtually no heat to the Earth. So heat's coming in from the sun and going out to the wilds of space. And the Earth radiates that heat away by the means of its own thermal radiation, which again is associated with its temperature. According to the Stefan Boltzmann constant, the Earth's outgoing thermal radiation is proportional to the 4th power of the Earth's temperature, in this case, the surface temperature of the Earth. And so as the Earth gets hotter and hotter because of the sun putting heat into it, it gets better and better at radiating away heat. And they have long since reached a balance, where the Earth's surface temperature is just right to send heat out as fast as heat is coming in from the sun. This assumes an emissivity issue. We can say that the Earth is a black object, that it's infinitely good at, perfectly good at emitting its own thermal radiation, so its emissivity is 1. All right, in this hypothetical world, what is the surface temperature at which the Earth reaches this balance? And it's about minus 15 Celsius, 15 degrees Celsius. So it's cold. It's more like 0 degrees Fahrenheit, give or take. Well, that's pretty cold. We're not at that temperature on average. How's that? Well, at minus 15 C, the Earth will be radiating away its heat exactly as fast as the heat is coming in from the sun. And that would be the surface temperature without the atmosphere. We really would be. It would be an ice planet. However, we do have an atmosphere, and the atmosphere is not inconsequential in this story. The Earth's atmosphere is relatively transparent to the sun's thermal radiation, not completely, but as we'll see. But the Earth heats up; it's receiving the sun's thermal radiation, as in my hypothetical atmosphereless planet. But now, if we put the atmosphere back in, we're still getting heat in from the sun. It's not changed significantly. And we're still radiating it away, pretty much as was. And so the Earth still has an effective radiating surface. As though it's a black object, it still has a radiating surface that has the same temperature as before, minus 15 C. But where is that radiating surface? It's not the ground anymore. It's on average, and this sort of blurs out all the details of how the Earth exactly radiates all the portions of its heat away. You can sort of blur it all out and say the Earth still is still a black object radiating away heat, and that black object has an effective temperature of minus 15 Celsius. But the effective location of that black surface isn't the ground anymore. It's up in the Earth's atmosphere. The Earth's atmosphere is not fully transparent, and it's certainly not fully transparent in the infrared. It's quite capable of interacting with thermal radiation in the infrared. And the result is that that effective location of that radiating surface is not ground level, it's rather about 5 kilometers up above ground level. And so it's about minus 15 C up there, high in the atmosphere. And down here, closer to the ground, the temperature is higher. And there is a gradient in the Earth's atmosphere, a gradient in temperature in the Earth's atmosphere. If it's minus 15 Celsius at 5 kilometers up, down here by where the Earth is, it's more like plus 15. Actually, the numbers, now I'm thinking the numbers actually are, it's minus 18 up there. That's the effective, that's the temperature at which the balance occurs between sunlight in and thermal radiation out. Minus 18, not minus 15. And down here, we get up to plus 15. And plus 15 Celsius is about the average temperature of the Earth. Average over all the seasons and all the places in the surface. We hit about plus 15. So the idea then is the Earth's radiating surface is not the ground, it's up there at 5 kilometers, and it is cold up there, and the balance is achieved. But down here, higher. Why is the air down here hotter? It's in part because if you take air up high, where it's got a very low density and low pressure, and you carry it down here, the surrounding air will compress it. The pressure is building up, so you have to squish the air together, pack it more tightly. And that packing process does work on the air and increases its temperature. So carrying air up and down in the atmosphere, it cools as it rises, it heats as it descends. We get a temperature gradient as a result. I mean, other ways in which you can think of it is for the air to have minus 18 Celsius way up high, where it's got a lot of gravitational potential energy. If you bring it down here, the gravitational potential energy has to become kinetic, thermal kinetic energy, and it's got to be warmer down here. Anyway, I leave the details of why there's a thermal gradient in the atmosphere for now, and just deal with, okay, down here it's hotter. Well, where does that how does that take us to climate change issues? Well, if you make the Earth's atmosphere darker, you increase its emissivity per liter. You make it harder to see through, better at exchanging through radiation. The effective location from which it will radiate away heat won't be 5 kilometers up anymore. It'll be higher. It'll be more like 6 kilometers. So if you darken the Earth's atmosphere, particularly in the infrared, you will allow it to radiate heat away better. The source of that thermal radiation will be at 6 kilometers, not 5. If that's true, then this thermal gradient that's naturally present in the Earth's atmosphere has more distance over which to act. And so you go from minus 18 way up high to, well, not to 15 here anymore. You got to 15 at a kilometer up. By the time you get down here, you got another couple degrees. In fact, about 6. So this scenario is bad news. Down here, instead of being 15 Celsius on average over the seasons, it would be more like 21 or 22 degrees Celsius over the seasons. We would be really hot. So, long and short of it is, as humankind gradually darkens our atmosphere by putting more things into the atmosphere that interact with electromagnetic waves, notably carbon dioxide, we make it so that the Earth's atmosphere becomes better at radiating away thermal radiation. And the effective location of its black body source, where does its thermal radiation start from? That moves to higher altitude. And as that moves to higher altitude, we get hotter down here, below it. So not a good thing. And whether humankind can stop this progression or not will be seen. So that then is the story of clothing, insulation, and climate, and I'll end the story.